Hi, my name is Ademola, and this is a project presentation on mapping fluoride contamination risk in Dockum Aquifer. Fluoride occurs in groundwater either naturally or through human activities. According to EPA, 0.7 to 1.2 milligram per liter is the desirable limit for fluoride in drinking water. Our study area is the Dockum Aquifer, which is a confined and also an unconfined aquifer, which covers about 35,000 square miles in about 46 counties in Texas. Some of the uses of groundwater, Dockum Aquifer groundwater, is irrigation, municipal water supply, and oil field waterproofing. Our objective in this project is to use logistic regression and naive Bayes classifier to develop test accident vulnerability model using the actual data we obtained from the aquifer. We use KNN model, which combines predictions of our logistic regression as well as a naive Bayes classifier to obtain a uniformly graded data set of fluoride vulnerability across the entire aquifer. We also integrated these two, the results or the predictions from these two models into a single final vulnerability map.
Hi, my name is Deseyi D John, and today I'll be talking about the parameters that we use to feed our models. So we were able to get our average flow rate from the CWD database, and we also got our well depth from the same database, and we were also able to get the normal annual precipitation for 30 years. We also made use of the mean annual temperature for 30 years too, and we're also able to get the land cover data from the MRLC. And then we also went to the Sorgo database to extract data for our well locations. We queried this database by linking multiple data together in the Sorgo database using Python with the help of GeoPanda and Fiona. This can also be done using QGIS. Basically what we did was that we linked the mu polygon to map unit to component to CH horizon, where we got some data from there, and to the CH texture group, and then to the CH texture we also got some more data from there too. So these are the data that we were able to get from the Sorgo database. We have the slope, elevation, and so on and so forth. We also have the EC, which is the electric conductivity. These data had a mean and maximum value, and also a representative value, which is the arithmetic mean. And we also got the soil texture from the MRLC, and the soil texture from the Sorgo data, and the land use code from the MRLC. We had to recode these because these are categorical variables. For the land use code, we were only interested in the land use that had the code of 82 or 3 as we recorded. And for any well location that had that code, we had assigned the value of 1, and for every other one we assigned the value of 0.
Hello, I'm Aalok. So that now we have all the potential list of predictor variables ready into a data frame. Now we want to select a subset of those variables that can best predict our Y variable of interest, that is fluoride exceedance above 1.5 milligrams per liter. So while doing that selection of independent variables, we're following certain rules. Number one being domain knowledge. So we're giving more focus to the parameters that we think are correlated with fluoride exceedance, may it be precipitation, higher precipitation leading to higher infiltration, so higher amount of fluoride can leach into the groundwater through soil or through the weathering of the rock deposits, or may it be presence of highly acidic soil in a region that helps leaching of the fluoride into the groundwater. But while doing that, we're also looking at the correlation between the variables. We don't want there to be a multicollinearity among the variables, but we want there to be some sort of correlation between predictor variable and our fluoride exceedance. And to guide us select independent variables, we also looked at feature importance using random forest regressor and decision tree regressor to get a bunch of parameters with higher importance value. So this plot of correlation here shows the correlation among the variables. For example, let's say this KSAT is highly correlated with liquid limit. So if I'm trying to implement them into my model, I'll not select both of those parameters because that will introduce multicollinearity into the model. And this is the correlation between each of our x variable, potential x variable, and average fluoride. So highly correlated variables, I'll try to include those parameters into the model, given that they are not collinear with other parameters that are in the model. So this is the random forest regressor and decision tree regressor I was talking about. So this helps us get a bunch of so highly ranked in terms of importance variables, or subset of 5, 6 can be taken into the model, and I'll rank them. I'll look at the toply ranked variables, and it will be selected such that they are not collinear with each other. So by performing all of this, these were the 10 variables I landed upon while avoiding multicollinearity and trying to get the variables with higher importance. So this is the logistic regression model that was set on these parameters to predict the fluoride exceedance, and these were the results. All the results are presented here. This is the confusion matrix and ROC curve for training data set, and this side is for the testing data set, and these were the accuracy, precision that were measured, and the same thing was performed by using the naive Bayes classifier for the same set of variables, and exactly the same result parameters were obtained so that we could look into the compare the results of logistic regression and naive Bayes classifier. So here, this was the result. These are different performance matrices and training data set for logistic regression and naive Bayes classifier. So we can see that both of them have same prevalence on the training data set, but in terms of accuracy, that is the ability of the model to predict true values, logistic regression is slightly better than naive Bayes. And both of the models seem to perform similarly on different aspects of the confusion matrix. And one thing to note here is alarmingly high rate of false positive in both of these models. That means our model is predicting our groundwater to be exceeding the given fluoride contamination level, even though they are not. So disadvantage of that is we might not end up using that water because of this model, when in reality that water is safe to use. So after doing this, we fit a KNN model. Our objective is to fit the KNN model to get a vulnerability map throughout the domain of the aquifer. So while doing that, during the fitting process of the KNN model, we need to calculate the distance between the wells or different points in our aquifer where we want to calculate the risk value. So to do that, given that our wells coordinates are given in latitude and longitude, we're using Haber-Sine function to calculate that length, because this takes into consideration of the Earth's curvature by using this formula, and a function Haber-Sine was created in Python. So here, before fitting the model into the KNN, first thing we did was to split the data into training and testing. We created a fishnet of 5 by 5 mile, and here the objective is to get a training data set such that all the wells in the training data set are from uniquely different fishnet IDs. So uniquely different square boxes here. So for example, if a box has more than one well, one of them will be randomly selected and put into the training data set, and rest of the wells on that box will be put into the testing data set. So to perform that, I used a fishnet of 5 mile by 5 mile, because while doing that, it gave us a split of around 75% in training and 25% in testing, which could be used for training testing split. And this was the code I used where I grouped by fishnet IDs that are assigned to each wells and selected at random for the training dataset, and all the remaining dataset wells were sent to testing. And while doing this, n neighbor value of 5 was taken, meaning 5 of the nearest wells were taken into consideration while measuring a risk value for a well. And Haber-Sine function created earlier was used as a metric with weighted distance, meaning nearest well has higher impact. So this was the result after fitting KNN, where we can see that when for the logistic regression predictors, as a y variable, it's doing fairly good job with one outlier here, and a similar where y variable was used from the naive Bayes classifiers probabilities. So this was the final risk vulnerability map that we obtained, and in here Since both logistic regression and naive-based models were performing with similar performance metrics, we created a model averaging ensemble. And the intuition behind this approach is that both models are likely making some correct predictions and some incorrect predictions, but their errors are likely to be uncorrelated. So by taking the average of both of them, we are effectively trying to smoothen out the errors and reduce the variance in the ensemble's prediction.
In creating our logistic regression model, we splitted our data into training and testing data, given 75% to training and 25% to testing. We instantiated our model using the C hyperparameter, fitted the model with the data set, the training and the testing data set, respectively. And then we masked the model to make predictions based on the training and then the testing model. The C hyperparameter helps to regularize our data sets. High or large values of C means that our models are weakly regularized or has weaker regularization. And then our model is also going to produce or likely going to produce lower bias and or the model will have lower bias as well as higher variance. And also small values of C means we have stronger regularization, simpler model, higher bias, and lower variance. From scikit-learn, we learned that the default value for C is actually 1.0, and values that range from 10 to 1,000 or more are considered large values of C. We obtained confusion matrix for our linear regression, and we are able to compare the confusion matrix of our training data set and our testing data set. In evaluating our logistic regression, we obtained about 65% accuracy for training, 73% accuracy for testing, 65% precision for training, 82% precision for testing, and it was 85% for recall for training, 74% recall for testing. The naive-based classifier showed increase in our training data sets, increase in accuracy, precision, and recall between our training and testing data sets. We fitted the result or the predictions from our logistic regression into, as well as the naive-based classifier predictions into our KNN models. And in creating a vulnerability map, we assign more importance to the values or the predictions of our logistic regression and lower weight to our naive-based classifier.
We're talking about my three models, which are the logistic regression model, the naive-based model, and the KNN model. These are the parameters that I use in fitting my model. On the right here, that is the correlations between these parameters. After fitting my logistic regression, I got an accuracy for the training data set of 71.8 and for the testing data set of 63.9. For the precision, I got 58.3 and 58.2 for the testing. For the recall, I got 31.8 and 31.6 for the testing. And I was also able to plot a confusion matrix for both the training data set and the testing data set, and I did the same thing too for the ROC curve for the training data set and the testing data set. Then after that, I was able to, this is my naive-based model. This is on the top right here, this is the code that I use in running the naive-based model. I use the Gaussian naive-based code, and I created the object, fits the model, and made my predictions using my training data set, and I also did the same thing using the testing data set. Basically, these naive-based models are used for classification tasks. They work by estimating the probability of a given input belonging to a particular class based on the frequency of the feature in the input. They assume that the features are independent of each other, which is kind of why they're called naive-based. So after doing that, I was able to get the accuracy, precision, and recall of 61.3 for the training data set and 73.2 for the testing data set. And for precision, I got 41.9 and 58.9 for precision for the testing data set. And for the recall, I got 61.8 and 76.8 on the testing data set. I also plotted a confusion matrix and an ROC curve for the naive base. So after doing this, I moved to my KNN model and I made a plot for the risk prediction of KNN model against the risks obtained from the logistic model. And also I did the same thing too but just this time I used the naive Bayes model. So this is what the plot shows us. um I then I then assigned weights to my logistic regression and my naive Bayes. I assigned more weights to the naive Bayes because I felt the naive Bayes performed better. The parts in the map here that shows dark red, that shows deep red, are the parts that are more vulnerable to fluoride, and the ones that are blue here are the ones that are least vulnerable. So basically, in conclusion, fluoride vulnerability exceeding 1.5 were mapped based on the selected set of input parameters. Northeast and central portion of Dockum is more vulnerable to fluoride contamination. Map shows the final ensemble of all the models with equal weightage. So what we did was that we combined our three models, and then we assigned equal weights to them, and then we try to see what the plot is going to be like. And this is what we got. Thank you very much.